Welcome to this comprehensive guide on AI architecture and game development, designed specifically for beginners. We'll explore how to create intelligent and engaging non-player character behaviors that truly bring your game worlds to life. This tutorial will cover fundamental concepts and practical applications, ensuring you gain a solid understanding of AI in games. Today, we'll demystify 3 fundamental techniques crucial for designing dynamic game agents: decision trees, finite state machines, and behavior trees. These methods are widely adopted in the industry for their effectiveness in managing complex NPC logic. These tools provide a structured approach to managing complex decision-making processes, allowing NPCs to react intelligently and dynamically to their environment. By understanding these architectures, you can craft more believable and responsive game characters. First, let's delve into decision trees. These are flowchart-like structures that guide NPCs in making decisions based on specific criteria. They offer a straightforward way to model conditional logic, making them an excellent starting point for AI design. Each node in the tree represents a decision point, leading to different outcomes based on the NPC's current state or various environmental factors. This branching logic allows for a clear and predictable decision-making process. For instance, an NPC might use a decision tree to determine whether to attack, flee, or take cover based on the player's proximity and the NPC's health. This allows for nuanced reactions to immediate threats and opportunities within the game. Decision trees can be implemented using nested if-then-else statements, a common and accessible approach in programming. This method is intuitive for developers familiar with basic conditional logic. Alternatively, a graph-based data structure can be used, where internal nodes hold pointers to predicate functions and leaf nodes hold pointers to action functions. This approach offers more flexibility and scalability for complex trees. The advantages of decision trees include their speed, ease of implementation and debugging, and their simple, intuitive nature. They are particularly effective for scenarios where decisions are clear-cut and based on a limited set of variables. However, complex decision trees can become unwieldy and hard to maintain, especially as the number of decisions grows. This can lead to a spaghetti code scenario, making updates and modifications challenging. They may also lack the capacity to model highly complicated behaviors, limiting their application in advanced AI. For truly dynamic and emergent behaviors, other architectures might be more suitable. Next, we explore finite state machines, or FSMs, which are computational models defining an object's behavior based on a finite number of states. FSMs are fundamental in game AI for managing distinct behavioral modes. Each state represents a different condition or mode of the system, such as idle, walking, or attacking. These states encapsulate specific behaviors and responses, providing a clear structure for NPC actions. Transitions between these states are triggered by specific events or conditions, like player input or a timer. This event-driven nature allows NPCs to react dynamically to changes in the game world. FSMs are commonly used to manage AI states, ensuring that each entity behaves predictably within the game. This predictability is crucial for creating a consistent and understandable player experience. For instance, a guard NPC might transition from a patrolling state to a chasing state when it spots the player. This immediate and logical response enhances the realism and challenge of the game. FSMs can be implemented using enums and switch statements in C#, providing a straightforward way to manage states. This method is easy to understand and implement for basic state management. A more object-oriented approach involves using interfaces and classes for each state, promoting modularity and reusability. This allows for cleaner code and easier expansion of complex state behaviors. The advantages of FSMs include their ease of understanding, implementation, and debugging, offering a clear way to manage behaviors. Their explicit state transitions make them highly predictable and testable. However, FSMs can become complex and inflexible as the number of states and transitions increases, making management difficult. This can lead to a state explosion problem, where the FSM becomes unwieldy. Finally, we introduce behavior trees, or BTs, a hierarchical model for controlling AI decision-making. BTs offer a powerful and flexible alternative to FSMs, especially for intricate NPC behaviors. BTs consist of nodes representing different behaviors or actions, organized in a tree structure, traversed from top to bottom. This hierarchical organization allows for complex behaviors to be broken down into manageable subtasks. Each node evaluates its conditions and executes its actions, providing a flexible and modular system. This allows developers to easily add, remove, or modify behaviors without disrupting the entire AI system. BTs are more modular, scalable, and reusable than FSMs, making them ideal for complex AI behaviors. Their ability to handle multiple concurrent tasks and priorities makes them suitable for sophisticated NPCs. For example, a BT might allow an NPC to patrol an area, search for enemies, and engage in combat, with each behavior as a separate branch. This enables a rich tapestry of actions and reactions within a single AI agent. BTs are implemented using composite nodes like selector and sequence, and leaf nodes for actions or conditions. These node types provide the fundamental building blocks for constructing complex behavioral logic. A selector node executes child nodes until one succeeds, while a sequence node executes child nodes in order until one fails. Understanding these core node types is key to designing effective behavior trees. The advantages of BTs include their modularity, scalability, and ease of design, testing, and debugging. Their visual nature often simplifies the process of understanding and modifying complex AI logic. They provide a visual way of modeling AI decision-making, which aids in understanding and collaboration among development teams. This visual representation can significantly reduce development time and errors. However, BTs can be more complex to implement initially compared to simpler decision trees or FSMs. The learning curve for understanding their hierarchical structure and node interactions can be steeper. These AI architectures can be implemented in Visual Studio using C# and seamlessly integrated into the Unity 3D engine. This powerful combination provides a robust environment for developing advanced game AI. Unity provides a visual scripting environment and an asset store with various AI tools and assets to streamline development. These resources can significantly accelerate the creation of sophisticated NPC behaviors. Visual Studio also offers extensions for viewing and debugging finite state machines, enhancing the development workflow. These tools provide invaluable insights into the real-time behavior of your AI. Now, let's walk through the step-by-step implementation of decision trees in Unity 3D. This practical demonstration will solidify your understanding of how these concepts translate into actual game code. First, define the decision criteria by determining the factors that will influence your NPC's decisions. This involves identifying all relevant game states and environmental variables that an NPC might react to. Next, create nodes for each decision point and action within your decision tree structure. Each node will encapsulate a specific test or an executable action, forming the building blocks of your AI. Then, build the tree by connecting these nodes to establish the complete decision-making flow. This involves defining the parent-child relationships and the conditions under which different branches are followed. Implement the specific actions that the NPC will take based on the outcome of the decision tree. These actions are the actual behaviors your NPC will perform, such as moving, attacking, or interacting with objects. Finally, integrate the decision tree into the NPC's script and update its behavior based on the tree's decisions. This typically involves calling the tree's evaluation method within the NPC's update loop. Now, let's move on to the step-by-step implementation of finite state machines in Unity 3D. This section will guide you through creating robust and manageable state-based AI for your game characters. Begin by defining the different states your NPC can be in, such as idle, patrol, chase, or attack. Clearly enumerating these states is the first step in structuring your FSM. Implement each state by creating classes that define the behavior and actions associated with that specific state. Each state class will contain the logic for what the NPC does while in that state. Determine the conditions that will trigger a change from one state to another, defining your transitions. These conditions are the rules that govern how your NPC moves between different behaviors. Create a state machine class to manage these transitions and the overall flow between states. This central class will handle changing the current state and executing the appropriate state logic. Finally, integrate the state machine into the NPC's script and update its behavior based on the current state. This ensures that the NPC's actions are always governed by its active state. Let's proceed with the step-by-step implementation of behavior trees in Unity 3D. This advanced technique will allow you to create highly flexible and modular AI systems for complex NPC behaviors. Start by defining the structure of your behavior tree, including the root node, composite nodes, and leaf nodes. This foundational step establishes the hierarchy and flow of your AI's decision-making. Implement the leaf nodes, which represent the actual actions or conditions the NPC will perform or evaluate. These are the atomic units of behavior, such as move to target or is enemy visible. Assemble the behavior tree by creating a new script to link all the nodes and execute the tree's logic. This script will manage the traversal of the tree and the execution of its nodes. Test and debug your behavior tree by placing your NPC in a scene with a target object and observing its reactions. Iterative testing in various scenarios is crucial for refining complex AI behaviors. To ensure optimal AI development, always start simple with basic behaviors and gradually increase complexity. This iterative approach helps in managing complexity and identifying issues early in the development cycle. Utilize visual tools to represent decision trees, FSMs, and BTs, as this greatly aids in understanding and debugging. Visual editors can provide a clear overview of your AI's logic, making it easier to identify and fix problems. Thoroughly test your AI in various scenarios to ensure it behaves as expected under different conditions. Comprehensive testing is vital for creating robust and reliable NPC behaviors that enhance the player experience. Monitor performance to avoid lag, especially in complex environments with multiple NPCs, ensuring a smooth player experience. Efficient AI design is crucial for maintaining high frame rates and overall game responsiveness. By understanding these AI architectures and following these implementation steps, game developers can create intelligent and engaging NPCs. These techniques empower you to build dynamic and immersive game worlds. These techniques will significantly enhance the player experience, making your games more immersive and dynamic. Intelligent NPCs contribute greatly to the believability and replayability of your creations. Thank you for joining us in this exploration of AI architecture in game development. Keep experimenting and building amazing games, pushing the boundaries of what's possible with intelligent non-player characters.